So, here is something worth sitting with as you settle in for the night. Right now, somewhere close and somewhere far away, hundreds of nuclear reactors are quietly operating. Inside each one, atoms are splitting. The heat from those tiny events is warming water, raising steam, turning turbines, and sending electricity into the grid, where it becomes the light above a kitchen table, the charge in a phone, or the steady power that keeps a hospital awake through the dark. It is a remarkable thing, especially when you remember that, little more than a century ago, nobody knew an atomic nucleus could split at all. The people who began this story were not trying to build power stations or weapons. They were trying to answer a much older question. What is matter made of? What lies inside the smallest pieces of the world? For more than 2,000 years, the atom was mostly an idea. The ancient Greek thinker Democritus imagined that if matter were divided again and again, eventually something indivisible would remain. He called it atomos, meaning uncuttable. Much later, in the early 19th century, John Dalton used the regular patterns of chemistry to argue that matter really did come in discrete units. Dmitri Mendeleev arranged the elements into the periodic table, revealing an order that seemed to arise from some hidden internal structure. Still, by the end of the 19th century, many scientists pictured atoms as tiny, solid balls. That picture began to crack in 1895 when Wilhelm Röntgen was experimenting with electrical discharges in glass tubes. He noticed that a fluorescent screen across the room glowed even though the known rays from his apparatus could not reach it. Something invisible was passing through the air and through solid material. He called the unknown radiation X-rays. When Röntgen placed his wife's hand between the tube and a photographic plate, the image revealed her bones and wedding ring beneath the flesh. It was eerie, intimate, and completely new. The photograph spread around the world and inspired scientists to search for other forms of invisible radiation. The following year, Henri Becquerel began studying uranium salts. He thought sunlight might energize the uranium and cause it to emit rays. His plan was to place the material on a photographic plate wrapped in dark paper and leave it in the sun. But Paris turned cloudy, so he placed the plate and uranium together in a drawer. A few days later, he developed the plate anyway. Instead of a weak image, he found a strong one. The uranium had fogged the plate in darkness. No sunlight had been required. Energy was emerging from the material itself. The discovery was taken further by Marie Sklodowska-Curie and her husband, Pierre. Marie tested one element after another and found that thorium also emitted radiation. Then she noticed that pitchblende, a uranium ore, was more radioactive than pure uranium. Something else had to be hidden inside it. The Curies worked in a drafty converted shed and processed tons of ore. Marie stirred great vats of chemically treated material with an iron rod almost as tall as she was. From that enormous mass, they isolated tiny quantities of two new elements: polonium, named for her homeland, and radium. Radium seemed almost magical. Its salts gave off a faint blue glow, as though some quiet fire burned inside them without fuel. But the researchers did not yet understand the danger. Marie carried radioactive samples in her pockets. Her notebooks remain radioactive today. Decades of exposure almost certainly contributed to the illness that ended her life. Radioactivity showed that the atom was not solid or indivisible. Something inside it could change, and energy could escape. The next decisive clue came from Ernest Rutherford. Around 1909, His team fired positively charged alpha particles at an extremely thin sheet of gold. According to the leading model of the time, the particles should have passed through with only gentle deflections. Most did, but a few turned through enormous angles, and some came almost straight back. Rutherford later compared it to firing a heavy artillery shell at tissue paper and having it return to strike you. The only explanation was that nearly all the atom's mass and positive charge were concentrated in a tiny, dense center. He called it the nucleus. The rest of the atom was mostly empty space. Rutherford later identified the proton, but the masses of heavier nuclei showed that something else must also be present. In 1932, James Chadwick discovered the neutron, a particle with almost the same mass as a proton, but no electrical charge. That lack of charge would become crucial. A positively charged particle approaching a positive nucleus is repelled. A neutron is not. It can pass through the electrical barrier and enter the nucleus almost as if walking through an open door. Once inside, it can disturb the delicate arrangement holding the nucleus together. The person who helped reveal what could happen next was Lise Meitner. Meitner was born in Vienna in 1878 and became fascinated by physics at a time when women were excluded from much of academic life. She studied privately, earned a doctorate, and moved to Berlin, where she began a partnership with the chemist Otto Hahn. At first, she was forced to work in a basement workshop because women were not permitted in the main laboratories. She was unpaid for years. Still, she became one of Germany's most respected physicists. For 3 decades, Hahn performed delicate chemical separations while Meitner interpreted what the results meant inside the atom. Their partnership survived professional barriers, war, and political upheaval. But it could not escape the rise of Nazi Germany. Meitner came from a Jewish family. After Germany annexed Austria in 1938, the limited protection of her Austrian citizenship disappeared. With help from colleagues, she fled across the border carrying little more than 10 marks, and a diamond ring Max Planck had given her in case she needed to bribe a guard. She eventually found safety in Sweden, separated from her laboratory and from the work that had defined her life. Back in Berlin, Hahn and the younger chemist, Fritz Strassmann, continued bombarding uranium with neutrons. Scientists expected the uranium nucleus to absorb a neutron or perhaps lose a small piece. Instead, the chemical evidence pointed to something impossible. Among the products was barium, an element far lighter than uranium. Hahn trusted the chemistry but could not explain it. In December of 1938, he wrote to Meitner, describing the result and asking for help. He wondered whether the uranium nucleus might somehow have burst apart. Meitner read the letter while staying in a small Swedish town over Christmas. Her nephew, the physicist Otto Frisch, was visiting. Together, they considered the uranium nucleus using the liquid drop model. A heavy nucleus can be imagined as a tiny drop held together by the strong nuclear force. That force is extraordinarily powerful, but it acts only across very short distances. At the same time, the many positively charged protons repel one another across the nucleus. In uranium, these two effects exist in a delicate balance. When a neutron enters uranium-235, the nucleus gains energy and begins to wobble. It stretches. The two ends pull farther apart, weakening the short-range force that holds them together while electrical repulsion continues pushing them away. If the deformation becomes great enough, The nucleus pinches in the middle and separates into two smaller nuclei. Meitner calculated the energy involved using Einstein's relation between mass and energy. The two fragments together had slightly less mass than the original uranium nucleus and an incoming neutron. The missing mass had become energy, roughly 200 million electron volts from a single fission. A chemical reaction releases only a few electron volts per atom. Nuclear fission releases tens of millions of times more. The scale was almost difficult to believe. Frisch gave the process a name borrowed from biology, where a cell dividing into two is said to undergo fission. Hahn and Strassmann published the chemical evidence. Meitner and Frisch published the physical explanation. Within weeks, laboratories around the world confirmed it. Then came the realization that made the discovery far more consequential. A uranium nucleus does not split into only two fragments and energy. It usually releases two or three additional neutrons. Those neutrons can strike other uranium nuclei, causing more fissions and releasing still more neutrons. A chain reaction was possible. The idea had occurred to the Hungarian physicist Leo Szilard years earlier. In 1933, while waiting at a traffic light in London, he imagined an element that released more than one neutron after absorbing one. If such an element existed, one reaction could produce two, two could produce four, and the number could rise rapidly. He even patented the concept and placed it under secrecy because he understood its military potential. Now fission had supplied the missing element, and Europe was moving toward war. Szilard feared that German scientists might build a weapon first. In the summer of 1939, he visited Albert Einstein and explained the danger. Together with fellow physicists, they prepared a letter to President Franklin Roosevelt warning that uranium chain reactions might make bombs of extraordinary power possible. The first American response was cautious and slow. A committee was formed and a small amount of money was assigned to research. But in Britain, two refugee physicists, Rudolf Peierls and Otto Frisch, performed a calculation that changed the sense of urgency. Many had assumed a bomb would require tons of fissile material. Peierls and Frisch showed that a practical weapon using purified uranium-235 might need only kilograms. Their memorandum described the likely blast, heat, and radioactive contamination with the calm precision of an engineering report. The British Maud Committee examined the problem and concluded that a bomb was feasible. When its findings reached the United States, and especially after the attack on Pearl Harbor in December of 1941, the project accelerated. The question was no longer whether the energy could be released. The question was whether an entire industrial system could be built quickly enough to release it before the war ended. By 1942, the effort had become the Manhattan Project. Directed by General Leslie Groves, Groves had recently overseen construction of the Pentagon. He was demanding, impatient, and accustomed to projects so large that ordinary management methods no longer applied. Under him, the work expanded into secret laboratories, factories, and entire new towns. The physics of fission was understood. Producing enough suitable material was the harder problem. Natural uranium contains mostly uranium-238. Only about 0.7% is uranium-235. The isotope that readily sustains the kind of chain reaction needed for a weapon. The two isotopes are chemically identical. Their main difference is 3 neutrons and a tiny difference in mass, so ordinary chemistry cannot separate them. The project pursued several methods at once. At Oak Ridge, Tennessee, uranium was converted into the corrosive gas, uranium hexafluoride, and forced through barriers containing microscopic pores. Molecules with uranium-235 moved through very slightly faster than those with uranium-238. The advantage in a single stage was almost nothing, so the gas had to pass through thousands of stages in an immense cascade. The K25 gaseous diffusion building was half a mile long and, for a time, the largest roofed building in the world. Its pipes had to remain perfectly sealed against a gas that reacted aggressively with moisture. New pumps, coatings, barriers, and seals were designed while the plant itself was already being built. Another facility, Y12, used electromagnetic separation. Ionized uranium passed through powerful magnetic fields, causing the lighter and heavier isotopes to curve along slightly different paths. These machines were called calutrons. Copper was scarce during the war, so the magnets used thousands of tons of silver borrowed from the United States Treasury. The calutrons were operated largely by young women recruited from the surrounding region. Most were never told what they were producing. They watched gauges, adjusted controls, and followed carefully prepared instructions. To the surprise of some scientists, they often operated the machines more consistently than the physicists, who were tempted to keep experimenting with the controls. The operators simply kept the system steady. The project also pursued plutonium, an element that barely exists in nature and had to be manufactured inside a reactor. When uranium-238 absorbs a neutron, a sequence of radioactive changes can transform it into plutonium-239, which is fissile. But producing it required something humanity had never built: a reactor capable of maintaining a controlled chain reaction. That first step took place beneath the stands of a disused squash court at the University of Chicago. Enrico Fermi and his team assembled layers of uranium and graphite into a structure they called Chicago Pile 1. The graphite slowed neutrons, making them more likely to cause further fissions. Cadmium control rods absorbed neutrons and allowed the reaction to be regulated. The pile contained hundreds of tons of material. It had no modern containment building and almost no shielding. One emergency team waited above it with containers of neutron-absorbing solution, prepared to pour them over the structure if the reaction escaped control. On December 2, 1942, Fermi ordered the control rods withdrawn in careful stages. Neutron counters climbed. He calmly calculated how the reaction should behave and compared each prediction with the instruments. When the final rod reached the planned position, the multiplication of neutrons became self-sustaining. For about 28 minutes, humanity maintained its first controlled nuclear chain reaction. The power was only about half a watt, but the amount did not matter. The principle had been proved. Arthur Compton telephoned James Conant with a coded message. The Italian navigator, he said, had landed in the New World. Asked how the natives had behaved, Compton answered that they had been very friendly. A small graphite pile beneath a stadium was only the beginning. Industrial production required reactors operating at vastly higher power, with cooling, shielding, and systems for loading and removing fuel. The production site was built at Hanford in Washington state, where the Columbia River could provide abundant cooling water. DuPont was chosen to design and construct the reactors. The physicists calculated that about 1,500 fuel channels would be enough. DuPont's engineers insisted on adding hundreds more. To the scientists, the extra capacity appeared wasteful. To the engineers, it was protection against the things nobody yet knew. That margin saved the project. When Hanford's B reactor started, in September of 1944, it ran for several hours and then began losing power. The chain reaction was being poisoned by xenon-135, a fission product with an extraordinary ability to absorb neutrons. The effect had not been included in the original calculations. Because the reactor had extra channels, more uranium could be loaded and the increased reactivity overcame the poisoning. The episode became a lasting lesson in nuclear engineering. Theory describes the known world. Engineering must also leave room for corrosion, drifting instruments, imperfect materials, and isotopes that appear unexpectedly. Safety margins exist for what has not yet been imagined. While Oak Ridge and Hanford produced material, another laboratory had to design the weapon itself. That work took place at Los Alamos on a remote mesa in New Mexico, under the scientific leadership of J. Robert Oppenheimer. Oppenheimer was not chosen because he was the world's greatest specialist in one narrow field. He was chosen because he could understand many fields at once. He could listen to theorists, chemists, metallurgists, explosives experts, and engineers, then see how their work fitted together. Groves, whose manner could hardly have been more different, recognized that ability. The central problem was speed. Once fissile material becomes supercritical, each generation of fission creates more neutrons and more energy. But that energy immediately begins forcing the material apart. As soon as it expands enough, the chain reaction stops. The material, therefore, has to be assembled into a supercritical state so quickly that many generations of fission occur before the device destroys its own geometry. For uranium-235, the solution was a gun-type design. One subcritical piece would be fired down a barrel into another. The combined shape would become supercritical, and the reaction would grow. The weapon was called Little Boy. Its designers considered the principle simple enough that they did not plan a full-scale test. Plutonium created a deeper problem. Material from Hanford contained plutonium-240, an isotope that undergoes spontaneous fission and releases stray neutrons. A gun assembly came together too slowly. A neutron could begin the chain reaction before the pieces were fully joined, producing a weak premature explosion known as a fizzle. The entire plutonium effort seemed threatened until Los Alamos turned toward a much more difficult idea: implosion. Instead of bringing separate pieces together, a sphere of plutonium would be surrounded by conventional explosives. When those explosives detonated, they would compress the sphere inward from every direction. Greater density reduces the amount of material needed for criticality, so the previously subcritical core would become supercritical during compression. The idea was elegant. The required symmetry was unforgiving. If one side arrived slightly before another, the plutonium could distort and escape through weak regions instead of compressing evenly. George Kistikowski and his explosives team developed shaped combinations of fast and slow explosives, called explosive lenses. Like a glass lens bending a wave of light, these carefully formed blocks reshaped detonation waves into a sphere converging toward the center. 32 detonators had to fire almost simultaneously. The explosive blocks had to fit with extreme precision. At the center sat the plutonium pit, roughly the size of a grapefruit, surrounded by a heavy tamper that reflected neutrons and helped hold the compressed core together for a tiny fraction longer. A small initiator produced a burst of neutrons at the moment of greatest compression. There were too many ways for the system to fail without a test. In July of 1945, the device, known simply as the gadget, was raised to the top of a steel tower in the New Mexico desert. The test was called Trinity. The night before the explosion, thunderstorms crossed the Jornada del Muerto. Rain struck the tower, and lightning flashed near equipment filled with delicate firing circuits. Oppenheimer waited exhausted and chain-smoking. Groves watched the weather. The scheduled time was delayed until the storm began to clear. At 5:29 and 45 seconds on the morning of July 16th, the signal was sent. The detonators fired. The explosive lenses created their inward-moving wave. The plutonium compressed. The initiators supplied neutrons. In about a millionth of a second, the chain reaction passed through scores of generations and released energy equivalent to roughly 21,000 tons of TNT. The desert became brighter than daylight. The steel tower vanished into vapor. Sand beneath it melted into a greenish glass later called trinitite. The mushroom cloud rose more than 40,000 feet, and the blast wave struck observers miles away like a physical blow. Fermi dropped scraps of paper as the pressure wave arrived and estimated the yield from the distance they moved. His rough calculation made in the desert wind came surprisingly close. Some observers cheered, some cried, some remained silent. Oppenheimer later recalled a line from the Bhagavad Gita about becoming death, the destroyer of worlds. The test director, Kenneth Bainbridge, offered a harsher judgment to Oppenheimer. Now we are all sons of bitches. Decades of patient science, industrial construction, ancient engineering had converged into one flash. The implosion design worked. 3 weeks later, on August 6th, Little Boy was dropped on Hiroshima. On August 9th, a plutonium implosion bomb called Fat Man was dropped on Nagasaki. The immediate destruction and the deaths that followed from burns, injuries, and radiation reached roughly 200,000 by the end of 1945, with later estimates varying by method and source. Japan announced its surrender on August 15th. The war ended, but the knowledge could not be returned to the laboratory. A nuclear weapon and a nuclear reactor rely on the same basic event, yet they pursue opposite goals. A weapon drives the chain reaction forward as rapidly as possible and releases the energy before the material flies apart. A reactor holds the reaction at a steady level, removing heat continuously and preventing sudden change. One is an explosion, the other is a carefully tended fire. The peaceful use of fission begins with heat. When uranium-235 splits, the two main fragments fly apart at high speed. They travel only a tiny distance through the fuel before colliding with surrounding atoms. Their motion becomes heat. That is the basic conversion inside every fission reactor. Fragments move, fragments stop, and the fuel grows hot. From there, the plant is surprisingly familiar. Coolant carries the heat away. Water becomes steam. Steam spins a turbine, and the turbine turns a generator. A nuclear power station is, in one sense, a highly sophisticated steam engine. The unusual part is the furnace. That furnace has extraordinary energy density. A small quantity of uranium can provide the energy of vast amounts of coal. A fossil fuel plant needs a continuous stream of trains, ships, or pipelines. A reactor can operate for many months between fuel changes. The possibility attracted the United States Navy, especially one officer named Hyman G. Rickover. Rickover was intense, abrasive, and almost impossible to satisfy. After studying nuclear technology at Oak Ridge in the late 1940s, he became convinced that a reactor could transform the submarine. Conventional submarines were mostly surface vessels that could hide underwater for limited periods. Diesel engines powered them on the surface, while batteries provided only a few hours of underwater operation before recharging became necessary. A nuclear submarine could remain below the surface for as long as food and human endurance allowed, but its reactor would have to be compact, powerful, and exceptionally reliable. A fault inside a land-based plant might lead to shutdown and repair. Deep beneath the ocean, it could threaten every person aboard. Rickover's most important contribution was not a single component, it was a culture. He demanded complete knowledge of systems, careful documentation, rigorous training, and personal responsibility. Parts were tested, inspected, and tested again. He believed that reactors became safe only when every person involved understood that apparently small decisions could carry enormous consequences. He also understood bureaucracy. Nuclear work belonged to the Atomic Energy Commission, while submarines belonged to the Navy. Rickover obtained positions in both organizations. When the Navy asked what the Commission was doing, Rickover could answer. When the Commission asked what the Navy required, he could answer that too. The arrangement gave one determined engineer control across an institutional gap that might otherwise have delayed the program for years. His team chose the pressurized water reactor. Ordinary water performs two useful jobs inside this design. It carries heat away from the fuel, and it slows neutrons. A fast neutron is less likely to cause another fission in uranium-235. Collisions with hydrogen nuclei in water reduce its speed, making the chain reaction easier to sustain. The water must remain liquid at temperatures far above its normal boiling point, so the primary circuit is held under very high pressure. Hot water leaves the reactor vessel and passes through tubes in a steam generator. On the other side of those tubes is a separate lower pressure supply of water. Heat crosses the metal walls and boils the secondary water into steam. The primary water, which has passed through the reactor core, remains sealed within its own loop. The steam reaching the turbine belongs to the separate secondary loop. This separation keeps most of the power machinery away from radioactive coolant and allows each part of the system to be designed for its particular task. Before placing the reactor in a submarine, Rickover built a full-scale prototype in the Idaho desert. It sat inside a replica of a submarine engine compartment, so engineers and sailors could test not only the reactor, but the routing of pipes, the position of valves, access for maintenance, and the way people would move through the cramped space. The prototype operated successfully in 1953. USS Nautilus was launched the following year and went to sea under nuclear power in January of 1955. It could travel submerged at speeds and distances that conventional submarines could not approach. In 1958, it passed beneath the Arctic ice and completed the first submerged transit of the North Pole. The pressurized water reactor then moved ashore. Westinghouse adapted the naval design for the plant at Shippingport, Pennsylvania, which began operating in 1957. It was modest compared with later stations, but it proved that a reactor could deliver dependable electricity to a civilian grid. Through the 1950s and 60s, optimism grew quickly. Utilities ordered larger plants, and reactor output climbed toward 1,000 megawatts. Yet, commercial expansion created pressures different from those of the naval program. The Navy placed reliability above nearly everything. Utilities also had schedules, budgets, investors, and competition. The Atomic Energy Commission had the awkward job of both promoting nuclear power and regulating it. At the same time, plant designs were increasing in size faster than experience was accumulating. Engineers had to imagine what could happen if cooling failed, pipes broke, valves stuck, or operators misunderstood their instruments. The central problem is decay heat. Control rods can stop the fission chain reaction within seconds, but the fragments already created inside the fuel remain radioactive and continue releasing heat. Immediately after shutdown, that heat can still amount to several percent of full reactor power. In a large plant, several percent means tens of megawatts. The core must therefore be cooled even after it has been shut down. If water no longer covers the fuel, temperatures rise. Zirconium alloy cladding can react with steam, releasing hydrogen and additional heat. Fuel can soften, deform, and melt. Preventing that sequence became the focus of layers of protection known as defense in depth. The ceramic fuel pellet holds many fission products within its structure. Metal cladding surrounds the pellets. A massive steel vessel contains the core. Around that stands a reinforced concrete and steel containment building. Pumps, water supplies, electrical systems, and emergency equipment are duplicated so that the failure of one does not remove every path to cooling. 3 accidents would later become major turning points in the history of nuclear energy. Their detailed sequences belong to the history of nuclear disasters. But here the important question is how each one changed reactor design, regulation, economics, and public trust. At 3 Mile Island in Pennsylvania in 1979, a combination of equipment failure, misleading indicators, and operator confusion led to a partial core meltdown. The reactor vessel and containment building prevented the accident from becoming a large public radiation disaster, and no death or injury was attributed to radiation from the event. Yet the accident exposed serious weaknesses in control room design, training, emergency communication, and the assumption that operators would always understand a complicated plant from a flood of alarms. Afterward, the industry redesigned displays, expanded simulator training, improved emergency procedures, and created stronger systems for sharing operating experience. Chernobyl in Soviet Ukraine in 1986 was fundamentally different. The RBMK reactor had dangerous characteristics at low power. The test was conducted under severely unstable conditions, and the plant lacked the robust containment structure common around many Western power reactors. Explosions tore open Unit 4. The graphite moderator burned, and radioactive material spread across large parts of Europe. The disaster revealed how a hazardous design could become far more dangerous when combined with secrecy, production pressure, weak independent oversight, and a culture that discouraged honest reporting. Remaining RBMK reactors were modified, international notification improved, and the nuclear industry began treating safety culture as seriously as hardware. Fukushima Daiichi in Japan in 2011 showed a third pattern. The reactors shut down after the earthquake, but the tsunami flooded electrical equipment and disabled several layers of backup power at once. Without reliable cooling, 3 reactor cores melted and hydrogen explosions damaged reactor buildings. Public radiation doses were generally far lower than at Chernobyl, while much of the broader human harm came from evacuation, displacement, interrupted medical care, and years of social disruption. The engineering lesson was the danger of common cause failure. A system may appear to have many backups, yet one flood, fire, earthquake, or other external event can defeat all of them if they share the same vulnerability. Together, the accidents changed the direction of nuclear power. 3 Mile Island emphasized human factors and readable control rooms. Chernobyl emphasized reactor physics, institutional honesty, and international transparency. Fukushima emphasized extreme natural hazards, station blackout, multi-unit emergencies, and backup systems that must not all fail in the same way. The policy effects were just as important. New construction slowed or stopped in several countries. Japan temporarily shut its reactor fleet for review. Germany accelerated its nuclear phase-out. And regulators elsewhere reassessed flooding, earthquakes, emergency power, portable pumps, batteries, water supplies, and crisis command systems. Nuclear plants that continued operating generally did so under stricter rules, stronger training, and more systematic oversight. These events did not produce one simple verdict on nuclear energy. They showed that severe accidents are possible, that their causes differ, and that public consequences extend far beyond radiation measurements. They also showed that design changes and institutional reforms can reduce risk, although no complex technology becomes perfectly safe. From that point onward, every debate about nuclear power had to balance its ability to produce large amounts of low-carbon electricity against cost, waste, construction difficulty, accident risk, and the quality of the institutions responsible for operating it. At the same time, the climate problem did not disappear. Nuclear plants continued supplying roughly a tenth of global electricity in the period bus described by the source text, and countries such as France demonstrated that a grid with a large nuclear share could operate with relatively low carbon emissions. This led to a more practical argument. Before building something new, keep safe existing reactors operating when possible. Closing a plant removes a large source of steady, low-carbon electricity. If wind, solar, storage, transmission, or other clean resources cannot replace it immediately, fossil fuels often fill the gap. New construction remains difficult. Large reactors require vast initial investment, long schedules, skilled workforces, stable regulation, and confidence that a project will not be redesigned repeatedly while it is being built. Safety systems add complexity, but so do financing, supply chains, political uncertainty, and the loss of experienced construction programs. Small modular reactors attempt to change that pattern. Instead of building one enormous plant almost entirely on site, the idea is to manufacture smaller standardized units in factories and assemble them where needed. A site could begin with one module and add others gradually. Smaller cores may also allow simpler passive cooling arrangements. The promise is repeatability. Build the same design many times, learn from each unit, and reduce cost through routine production. But promise and economics are not the same thing. NuScale received design certification in the United States, yet its first planned project in Idaho was canceled after projected costs rose. It was a reminder that a reactor can be technically credible and still struggle as a commercial project. Other concepts explore molten salts, high-temperature gas, cooling, or alternative fuel cycles. Some aim to remain safe without rapid human action. Some are designed to use fuel more efficiently or produce less long-lived waste. Each carries its own engineering questions involving materials, corrosion, maintenance, licensing, and cost. A beautiful diagram is only the beginning. A power plant must also operate every day, survive ordinary wear, and produce electricity at a price society will accept. And beyond fission is fusion. Fission divides heavy nuclei. Fusion joins light nuclei, usually forms of hydrogen, into heavier ones. It is the process that powers the sun. In principle, fusion offers abundant fuel and no self-sustaining chain reaction that can run away. If the extreme conditions are disturbed, the reaction simply fades. Those conditions are the difficulty. Atomic nuclei repel one another, so fusion fuel must be heated to temperatures above 100 million degrees, becoming a plasma. That plasma must then be compressed or confined long enough for significant fusion to occur. In December of 2022, the National Ignition Facility achieved a long-pursued milestone. A fusion target released more energy than the laser energy delivered directly to trigger it. The entire facility still consumed far more energy than the fusion produced. So this was not a practical power station. It was a proof that ignition could be achieved. In France, the International ITER project is constructing a much larger magnetic confinement experiment. Private companies are exploring other approaches. Fusion may eventually become part of the energy system, or it may continue to reveal new layers of engineering difficulty. Its future remains open. And so, as you lie here, perhaps drifting closer to sleep, we have traveled from an invisible philosophical atom to machines that manage the energy inside the nucleus. We followed Becquerel's photographic plate into a dark drawer. We watched Marie Curie stir tons of ore for a trace of radium. We sent Rutherford's particles through gold foil and found a nucleus where solid matter had seemed to be. We followed Lise Meitner into exile and watched an impossible piece of barium reveal that uranium had split. We stood beneath the stadium in Chicago as a chain reaction quietly sustained itself for the first time. We crossed the industrial cities of Oak Ridge and Hanford, then waded through the storm before the Trinity test turned desert night into day. We moved from weapons toward reactors, from Rickover's submarine prototype to shipping port, and from early confidence into the lessons of 3 Mile Island, Chernobyl, and Fukushima. The story is not simply one of progress, and it is not simply one of disaster. It is a story of immense physical power placed inside human institutions. The atoms behave according to physics. Everything around them depends on design, maintenance, communication, training, honesty, and judgment. That is why nuclear engineering is built in layers. Fuel is formed into ceramic pellets. Pellets are sealed inside cladding. The core sits within a heavy steel vessel. The vessel stands inside containment. Cooling systems are duplicated. Electrical supplies are backed up. Procedures are rehearsed. Operators watch instruments through quiet hours when nothing unusual is happening. Engineering, at its best, is applied worry. It is the patient work of imagining how a valve might stick how a cable might flood, how an instrument might mislead, or how several unlikely events might arrive together. Each lesson becomes another barrier, another alarm, another line in a procedure, another person trained to notice when the ordinary pattern begins to change. And tonight, somewhere beyond the room around you, water is moving through a reactor core. Heat is passing into a steam generator. A turbine is turning. Electrons are entering the grid and becoming the small, familiar comforts of modern life. The process is steady, patient, and mostly unseen. Atoms are splitting one by one, releasing energy stored since long before human beings existed. Control rods wait above the core. Pumps continue their measured circulation. In a quiet control room, someone is watching the instruments and confirming that everything remains where it should be. The history behind that calm is long. It contains curiosity and brilliance, ambition and fear, terrible destruction, costly mistakes, and careful learning. All of it is present, in a way, inside the quiet discipline of a reactor operating normally through the night. So let that image settle now. Water circulating, turbines turning, lights glowing in distant windows, and beneath it all the soft, steady hum of atoms doing their work while the world sleeps.